Okay, good day for everyone. My name is Xiao Yikan. Today I will present my investigation on the relationship between the length of a simple pendulum and its period of oscillation, as well as the determination of the local acceleration due to gravity. In the introduction part, a simple pendulum is an example of periodic motion under a small angle of oscillation such as under 15 degrees. It behaves as approximately as simple harmonic motion. The objective of this experiment was to investigate the relationship between the pendulum length and its period, determine the local acceleration due to gravity, and examine whether the mass of the bulb affects the period of oscillation. For the theory part, this equation is the period equation, which include the period of oscillation t, pendulum length L, and the gravitational acceleration, which is g. Since the relationship between t and L is non-linear, the equation was linearized by squaring both sides. Therefore, plotting a graph of t squared against L should produce a straight line. The gradient of the graph was then used to calculate the local acceleration due to gravity. For the data analysis part, in this experiment, for each pendulum length, two trials were conducted. The average time for 10 oscillations was calculated, followed by the period of one oscillation. The period values were then squared to obtain t squared, which was plotted against the pendulum length. For the result, this is the example graph for 10 gram, and it shows the manually plotted graph and the digital graph for the 10-gram bulb. Both graphs show a positive linear relationship between t squared and L. The calculated values of G are 9.87 mass per second square for the manual graph and 9.89 mass over second square for the digital graph. Both values are very close to the accepted value of 9.81 mass over second square. For the 25-gram bulb, both graphs also show a linear relationship. The manual graph gives a value of g, which is the local acceleration due to gravity, of 10.22 mass over second square, while the digital graph gives 9.87 mass over second square. The digital result is closer to the accepted value, whereas the manual graph shows a deviation due to experimental uncertainties. For the discussion part, by comparing all four example graphs of 10 gram and 25 gram, both the 10 gram and 25 gram bulbs produce similar values of G. This indicates that the mass of the bulb does not significantly affect the period of oscillation. This agrees with the theoretical derivation where the mass term cancels from the period equation, so the mass is independent of the period of simple pendulum. The initial angle of release was kept at approximately 8 de- degree throughout the experiment. This is important because at small angles the approximation sin theta almost equal to theta is valid when theta is measured in radians. Under this condition, the pendulum behaves approximately as a simple harmonic oscillator. So the theoretical equation can be applied with good accuracy. If a larger angle had been used, the approximation would no longer be valid, and the calculated value of G would become less accurate. For the example of Table A, it produced the most reliable result, with a calculated local acceleration due to gravity is 9.87 mass over second squared. Because the wider range of pendulum lengths, which is ranging from 20 cm to 80 cm, generate a larger spread of data point, allowing the gradient to be determined more accurately. For the table B, produce a larger deviation with a calculated local acceleration due to gravity is 8.69 mass over second squared because the shorter pendulum length, which is ranging from 20 cm to 50 cm, resulted in shorter oscillation times, making human reaction time contribute a larger percentage error. For the example of table C, the graph did not pass through the origin because only data between 50 cm and 80 cm were collected. Since all data points were collected between 50 cm and 80 cm, no measurements were obtained near the L equal to 0. As a result, the y-intercept had to be obtained by extrapolation, making it more sensitive to experimental uncertainties. By comparing manually graph and digital graph produce more reliable values because spotting and reading errors were reduced. In contrast, manual graphs were more susceptible to plotting inaccuracies and parallax errors, resulting in larger percentage errors. In this table, this is the data of the calculated local acceleration due to gravity. Most of the calculated value of g was slightly higher than the accepted value. This suggests that the measured periods may have been slightly underestimated, possibly due to human reaction time during stopwatch operation or slight underestimation of length of pendulum. In conclusion, the experiment confirmed a linear relationship between the square period and the pendulum length. The local acceleration due to gravity was successfully determined using graphical analysis. The results also show that the mass of the bulb does not significantly affect the period of oscillation. Overall, the experimental findings agree well with the theoretical model of a simple pendulum. Adult deviation were observed due to normal experimental uncertainties.